Hello and welcome. In this tutorial, we will have a look at 3D transformations with MVTec HALCON. In particular, we will learn how to read and use 3D poses and what makes them different from homogeneous 3D transformation matrices. The information presented in this video will help you with many applications, like hand-eye calibration, 3D measurements, or 3D surface comparison. Basically, a 3D pose describes the position and orientation of an object in space. A pose always relates to a specific coordinate system. In HALCON, we usually refer to the position as translation and the orientation as rotation. We call these transformations rigid because they do not change the shape or size of objects. Let's switch over to HDevelop for more details. When we create a pose, we can see that 3 parameters describe the translation in x, y, and z with respect to the origin of the reference coordinate system. Additionally, 3 parameters describe the rotation around x, y, and z. With all values set to 0, this pose represents the origin of the reference coordinate system. When we have values that are not 0, the resulting pose is transformed with respect to the reference coordinate system. Consequently, a pose can also be used for transformations of objects, or in other words, to move and rotate objects. Next, let's create a 3D box with this pose and visualize it. With the generic parameter disp pose, we can visualize the reference coordinate system. In general, in HALCON's 3D visualizations, the red arrow corresponds to the x direction, y is green, and z is blue. Now we create 2 poses with simple translations. To visualize them, we create arrows that start at the initial pose and end at the translation poses. The visualization looks like this. We can also combine these 2 transformations into one with pose compose. This is the result pose. In HALCON, poses are stored as tuples. The resulting translation arrow now looks like this. Note that pure translations can be combined in an arbitrary order. When we apply the translation to the box from before, we get a translated box. Next, let's have a look at rotations. Contrary to translations, the result of rotations differs if you change the sequence of rotations. Take a look at this example. Here we have 2 simple rotations. Depending on the order in pose compose, we get 2 different results. Note, however, that poses that look different can actually describe the same transformation. To check this, you can invert one of the 2 poses and then combine it with the other one. If the resulting pose contains only zeros, the poses describe the same transformation. The result here shows us that the 2 poses describe different transformations. If you want to reproduce a series of rotations around multiple axes, you can read pose rotations in 2 ways. If you read from right to left, the rotations are performed in the global coordinate system. Have a look at this animation. We first rotate around the global z-axis, then the global y-axis, and finally around the global x-axis. On the other hand, if you read the rotations from left to right, you rotate relative to the local coordinate system. In this visualization, we added a local coordinate system that is rotated alongside the actual object. As described, we first rotate around the local x-axis, then the local y-axis, and then the local z-axis. Note that you can change the interpretation of poses with various options. Have a look at the documentation of Create Pose for more information. We strongly recommend working with the default pose type. If you work with, for example, robots that use a different convention, Make sure to convert incoming and outgoing poses accordingly. Here we rotate the box with one of the result poses. As we have seen, there is an operator to invert poses. As another example, here we invert the translation and transform our box accordingly. As a result, we see the rotated box back at its starting position. Inverting poses is used often for another use case as well. Poses are frequently used to describe the position of one object in relation to another. For example, to describe the position of the camera from the robot's perspective, we commonly use this notation. You can interpret this notation as an arrow pointing from the first object to the second. This pose describes the position of the object as observed by the camera. With these two poses, we can compute the pose of the object as seen from the robot. To do this, we use pose-compose like this. The first object is also the first object of our result, and the last object is the second part of our result. The middle part of the input must be identical. As you can see, this notation makes using pose-compose straightforward. Sometimes another notation is used. This may be easier to read, but it makes pose-compose a bit more complex. As you can see, you can use poses in two ways mainly: the transformation of coordinates from one coordinate system to another, or the transformation of points inside a coordinate system. Additionally, we mentioned that poses can describe a rigid transformation consisting of translation and rotation. Besides poses, HALCON also offers homogeneous 3D transformation matrices. Homogeneous transformation matrices are much more powerful than poses. Just like poses, they can describe translations and rotations. Note that there are operators for working relative to local and global coordinate systems. Besides translation and rotation, transformation matrices can also describe a scaling. This is called an affine transformation. Every pose can be converted to a homogeneous 3D transformation matrix. Conversely, only homogeneous 3D transformation matrices describing a rigid transformation can be converted to poses. Here, to demonstrate an affine transformation, we translate, rotate, and scale our box. This concludes this video. HALCON includes even more 3D transformation operators, for example, for working with projective 3D transformation matrices, quaternions, dual quaternions, and Plücker coordinates. For much more information, please have a look at Chapter 2 of the Solutions Guide on 3D Vision titled Basics. Thank you for watching.